When entering the MedSmart demo for the first time, a message will appear with a basic description of how this software can help you on your plant. In order to open the demo file, you have to click on the Open button and then choose the MedSmart demo file folder. When using the demo for the first time, it is suggested that you work from left to right in the top ribbon. So we will start with number 1 and then work our way through all the different numbers. When the demo is opened, we are automatically in number 6, which is set conditions. Here we can set conditions for simulations. So when I click on number 1, I will do a quick review of how the flow sheet is drawn. So on this page, we can see the bottom ribbon, which is the library of equipment pieces. This library contains grinding, classification, and flotation icons. The next step is to click on number 2. The message here tells us that if we click on each equipment piece, we will be able to see the relevant structural dimensions and the limits. These values have already been entered previously for this specific demo. There are two main sections in the software. There's the blue section and the orange section. The blue section is if you have survey data and you want to mass balance it and build a mathematical model. The orange section is if you want to perform simulation studies. So when I click on number 3, survey data, I have two options here. Firstly, I can enter the survey stream data that has to do with the actual samples taken during the survey. So the feed sample and the slurry samples around the circuit. Secondly, I can enter information about each equipment piece during the survey. So we will do the slurry samples first. If I click on the blue button, I can see some information about the slurry samples and how to enter the properties. On the left hand side, we can see that currently we have the water balance switched on, the size distribution balance is switched on, and the assay balance is switched on. We are currently viewing the rates during the survey. So this information here is information that has been collected during the plant survey. Here I can see the percentage solids measurements of the slurry samples during the survey. If a sample was not measured, it is represented by a simple X. Here is the size distributions. Here again we can see that if a sample was not measured, we would represent it with an X. And then for the assays, for the flotation section we have chosen simply to choose a mineral. This would be copper or gold or PGMs or whatever method you are using in order to represent the composition of your ore when looking at flotation. So in this case we just generalized it and called it mineral. Now here we have our assays during the survey on our feed samples, and obviously you don't sample every stream for an assay around the grinding plant, but in the flotation section, we sampled the different concentrates and the tailings. After entering that data, we will check each equipment piece separately. I won't do all the equipment pieces, but as an example, we can look at the SAG mill and see here the information that we collected during the plant survey. So this is information about the operating variables as well as the permanent structure at the back of the mill in terms of the grades. An important equipment piece to look at here is the flotation cell. Now, this is the section where we can do laboratory float kinetics analysis. So here we have to enter our laboratory data, our times, as well as the cumulative percent recovery over time. On the right-hand side, we have full instructions on how to enter this data. After this data is entered, you can click on Calculate Kinetics, and then you'll automatically have your kinetics for the lab sample. It is important that when you do a plant survey, that you use the laboratory kinetics results for samples taken at the same time as the plant survey. Note here, we have 3 different rougher icons in the demo. This is actually the same rougher bank, but we are going to do an analysis on 3 different ore types. After the survey data has been entered and checked, we can mass balance it. When you mass balance, the process is quite quick. If we did this in Excel, it would have taken much longer. The reason for that would be that the recirculating loops in Excel requires a lot of processing power, but in the software it happens very quickly. So let's check a result for the mass balance. Here we are looking at the cyclone cluster results, and immediately we can see that there is a red result. In this case, we have a recirculating load of 306%. This number is quite high. Note that for this specific demo, this number was not available for measurements in the control room. So this is a number that was calculated during mass balancing. One of the reasons for mass balancing is to identify certain parts of the plant where the performance is not good, but it is also used to calculate the assays of the concentrates and the tailings to make sure how much you are removing from the plant and how much you are sending to the tailings dam. After performing a mass balance, we can calibrate the models. Now here the message tells us that we have constructed a mathematical model of the plant and that the calibration constant section is the important section in the results. So let's have a look at the SAG mill. In the SAG mill, we have calculated the breakage rates, a power draw constant, a slurry filling constant, and we've also calculated the actual ore hardness during the survey. This means that you don't have to send the sample away for a test in a laboratory. So the breakage rate shape that we are looking for is this type of shape here. If we look at the breakage rate, you can see that it follows a typical shape where the breakage rates go up to a maximum, then it comes down to the critical size. So this would be around 65 millimeters, and then the breakage rate goes up again into the bigger rocks where it breaks mostly due to abrasion. If we look at flotation, we can see that we have calculated the industrial kinetics. So this is the kinetics during the survey, and we've also calculated the scale-up factors. This can be used when we scale up laboratory kinetics to industrial scale kinetics. So if you are going to process a different type of ore in the future, you can do a lab test on that ore and then use these scale-up factors to make your predictions in simulation. So you can view every equipment piece in this flowsheet separately in order to assess its calibrated results. In the next step, we have to do simulations. So when you set a simulation, you will set the simulation scenario first. So you will set the feed that comes into the circuit, and then you will check each equipment piece to assess it for its operating variables, the amount of water that you add, and the conditions that you run the equipment under. Now note on the left-hand side that for the demo we added some scenarios that you can check. So there's 13 scenarios that you can follow in the demo, and we will make a separate video for each of these topics. After you've set your conditions, you will perform a simulation. And here you will see that we have some error messages.